was a little nervous when I found out there were going to be 500 people here, and then I learned that one person couldn't make it, so $4.99, and that's kind of reasonable. So I am Coraline Ehmke. I'm very happy to be in UK. You may not know this about me, but I'm actually an amateur ecologist. I've been tweeting all week since I got here with the ecology hashtag for the benefit of my colleagues back in America to share some facts with them about your country. That's absolutely true, I learned too. So I am a Rubyist. I've been doing Ruby since 2007 and the author of about 24 Ruby gems. You can learn all about my work at where.coraline.codes, which I think is the most awesome vanity URL ever. I'm on the Twitters as Coraline Ada. As mentioned, I'm the author of Contributor Covenant, which is the most popular open source code of conduct in the world with over 14,000 adoptions, including Rails, JRuby, and Elixir. You should take everything I say today with a grain of salt, since I'm speaking from the perspective of a liberal, progressive, transgender feminist who holds the controversial opinion that people should not be shits to each other online. So you've been warned. So we're going to talk about databases today. We have a lot of options when it comes to selecting a database, but in the Rails world especially, we always seem to reach for Postgres and Redis if we're feeling really experimental. So why is that? Traditional relational databases were designed to model paper forms and tabular data. You can easily imagine a table in a relational database being populated by a form in a GUI. But who says that tables are the best metaphors for how we store our data? We have a lot of options when it comes to databases and a lot of different kinds of databases at our disposal, and the one I want to talk about today is graph databases. So we'll start by answering the question, what is a graph database? Graph theory was pioneered by Leonard Euler in the 18th century and has been actively researched and improved upon by mathematicians, sociologists, and other scientists in the intervening centuries. However, it's only in the past few years that graph theory and graph thinking have been applied to information management. Part of it's driven by the massive commercial success of companies like Google and Facebook and Twitter, who use proprietary graph technologies to drive their solutions. But in recent years, we've also seen the introduction of general-purpose graph databases into the technology landscape. So what kind of data is suited to a graph database? Data with context. Data where, in order to understand the context, we need to name and qualify the connections between things. So in a graph database, there are two kinds of things that we're dealing with. We're dealing with nodes and with edges. Nodes are entities, and if you insist on thinking in relational terms, you can think of a node as a table, except that it's a table that can hold absolutely anything. It is object agnostic. And edges are relations. Relations are named, and they're directed, so they always have a start and an end node. Nodes contain key value pairs, and relations can also contain key value pairs. You can stick metadata on relations. Relations in a graph database are first-class citizens, which means that we can actually query on them, unlike join tables, which are not easy to query. So why would you choose a graph database? For intensive data relationship handling, graph databases have superior performance over relational databases. With a traditional database, query performance for relational data worsens as the number of records and the depth of the relationship increase. But with graph databases, performance stays linear and constant even as the data grows. The structure of a graph model flexes as our applications change and grow. Graph databases are schemaless, so that means that you don't have to mess around with a lot of migrations, and they're object agnostic. They don't care what kind of data is stored in a node. Graph databases are well suited for agile methodologies because we don't have to model the domain completely ahead of time, and we can change our mind. We can change the existing graph structure without modifying the data that we already have or the functionality that we already have. So there's some typical use cases, which I'm not going to get into right now. I'm gonna do this. It wouldn't be a graph database talk without talking about modeling a social network. It's actually a requirement, and I don't want to lose my license, so if you'll bear with me. In a relational database, we might model Twitter accounts this way, where there's a name and a handle, and of course an ID associated. And we might have a join table for followers with a follower ID, a person ID, and maybe some metadata like when they followed. In the graph database, we use nodes and edges. So nodes would contain users, and edges are the relation between users. So we might have a relation called follows, and we could stick the followed on metadata on that relation. But when two or more domain entities interact, like Coraline, Ada, and someone else interact on this example, facts emerge. Relations and metadata are facts, and we can represent these facts as separate nodes with connections to the entities engaged in the fact. So we might actually model it like this with a follow node where we have a relation between a person and a follow and another person. Once facts are represented as first-class citizens, we can ask questions like, how many people did someone else follow on December 31st? Or who has someone else been following for less than a month? Note that we're not interested in the kind of thing that's stored in a node. The graph database doesn't care. So we have things that can be described as users, we have things that can be described as follows, and another thing that, that we describe as relations, two different kinds of relations. And this is different from relational database where we'd have to store each of these things separately. So I want to talk today about NEO4J, which is a specific graph database. It was created by a company called Neo Technology. Neo4J is open source. It was written in Java. Interestingly, the native interface for Neo4J is over HTTP. And we're going to see an interesting side effect of that fact in a little bit. Neo4J was released in 2010. It comes in 3 editions. The community edition is free to use, but it's limited to a single node. Enterprise edition gives you clustering and hot backups and monitoring. And there's a government edition, which is like enterprise edition, but comes with some additional certifications. Neo4j is ACID compliant, which means it gives us atomicity, consistency, isolation, and durability, guaranteed reliable database transactions, unlike some other alternative databases. Neo4j stores graph data in a number of different store files. Each store file contains the data for a specific part of the graph. The division of storage responsibilities between these different files facilitates very highly performant graph traversals. So the node store is a fixed size record store where each record is exactly 9 bytes in length. Fixed size records enable fast lookups. If we have a node with an ID of 100, we know that its record begins 900 bytes into the file. And based on this format, the database can compute a record's location at O1 rather than having to search at O log n. Excuse me. So the first byte of a node is the in-use flag, which indicates to the database if there's data associated with this node or if it can be reused. The next 4 bytes are the ID of the first relationship connected to the node. The last 4 bytes represent the ID of the first property for the node. The node record's pretty lightweight. It's just a couple of pointers. The relationship store consists of also fixed-size records. In this case, each record is 33 bytes long. Each relationship record contains the IDs of the nodes at the start and the end of the relation, a pointer to the relationship type, and pointers for next and previous relationship records. This last set of pointers are part of what's called the relationship chain. So it's very efficient in its storage, and it's designed for high-performance operations and fast queries. So how do we query in Neo4j? We don't use SQL. We use a language called Cypher. And I'm going to walk through the CRUD verbs to show you what Cypher looks like. So our first operation is a create. We're creating a graphed person A with the name of Coraline and a handle of Coraline Ada. We'll also create a node B, which is the graphed person with the name of BathRuby and the handle of BathRuby with no spaces. Then to create a link between the two, a connection between the two, an edge, we match A and B, where A's name is Coraline and B's name is BathRuby. We create a follow relationship, and for the purposes of illustrating what we created, we'll return both nodes with the follow relationship in between. The thing that I wanted to point out with that particular query is that we're actually using ASCII art to draw a relation between A and B. There's an arrow because they're directional. We can actually draw which direction the connection goes in, which is pretty cool. So a read operation, we're going to match node A that follows node B, where node A's name is Coraline, and we'll return node A to follow in all instances of B. For an update operation, we're going to match node A with the name of Coraline. We're going to set A's name to code which, and we're going to return node A. Delete is a little bit more complicated. We'll match node A where A's name is Coraline. We're going to detach and delete A. Because a node has to have a start and an end, because an edge has to have a start and an end node, we can't just delete nodes. We also have to detach from all existing connections, all existing edges as part of that delete operation, which is what the detach does. So you're probably used to a database query interface that looks something like this for Postgres. What kind of console does NEO4J give us? This is pretty cool. This is where that native HTTP interface comes in handy. Neo4j's console is actually a single-page web app. Let's try a friends of friends query against our sample Twitter data set and see what that looks like. So we're going to match a follower, which is of type graphed person, with a connection that we're going to call follows, to a depth of 2, connected to nodes user, where the name of the user is Delore. And because we don't want to return a whole bunch of records, we're going to return the follower relationship, and the user, and we'll limit it to 100 records. Here's the cool part. Check that out. Isn't that awesome? So we get a graph. Because our data is graphical, why not get a graph back? So we can see the relations between the things. We can see the node we queried at the beginning in the center of the graph, and then the immediate followers, and then the followers of those followers, which is pretty cool. You can drag them around. You can double-click on them to see all the metadata that's associated with the node as well, which is pretty cool. And let's try it again with friends at a depth 3 and check out the performance. So I just tabbed up and entered the same query from history and changed the depth 2 to depth 3. Run it again, and it's still super fast. Awesome. So we're Rubyists, so how do we do Neo4j in Ruby? We use a gem, of course, neo4j.rb, which is an active model compliant ORM for the Neo4j graph database. Because it's active model compliant, if you know active record, you can get around pretty easily in neo4j.rb. So let's take a look at some code. This is, again, from our Twitter example. We have a graphed person. Notice that we're including Neo4j active node. So unlike active record, this is not an inheritance situation, which I actually like better. We're adding behavior to our class. We can define our class however we want, and we don't have to say that our class is an active record. So I like includes better for that sort of behavior. We declare a couple of properties. So this is a declarative schema. We declare a name, and we're going to index on name because we're going to be searching on it, and a handle record. And we define our relations. We have many outbound edges. We're going to call them followers, and we're going to relate to the class follower. In terms of our edge, we're including Neo4j active rel. I hate the fact that it's active rel instead of active relation. I think abbreviations in code are of the devil. But we mark the from class graph person, to class graph person, and the type or the label for the relationship is follows. You could add metadata properties here too if you wanted to. So in that graphed person, we had a method called friends to depth. So this is what it looks like when you build a Cypher query in your Ruby code. We're going to query as W, so this is just a handle to the query. We're going to match a follower with a follows relationship to a depth that we specify of a user with the handle of our handle. We're going to skip the direct relations and just go to the nested relations, and we'll return distinct followers by handle. And we are mapping to follower, and I'll show you, well, the reason we map follower is, first of all, the queries are lazily evaluated. So when you call that, you actually get a query object back. And when you do evaluate it, you get a struct And struct will have follower objects inside of it. So if you actually want to get at the records, you need to do a map. So let's see it in action from the REPL. So we'll take a graph person, just the first one, and assign it to GP. And we'll call GP dot, if I can type, friends to depth, and we'll specify a depth of 2. And there are graph people. And we can do depth 3, which is fast, and even depth 4, which is super fast. So that's pretty cool. So speaking of performance, how does the performance of NEO4J compare to a relational database? Again, if we're doing this friends of friends query, there was some research done, and this shows the depth on the very left, the time in seconds for a response from a relational database, time in seconds from NEO4J, and the number of records returned. So at a depth of 2, returning 2,500 records, performance between a relational database and a graph database is about equivalent. But you can see that the relational database gets worse and worse the greater the depth we go to. Now, to be fair, Postgres has added recursive queries, which improve the performance of queries like a friend-to-friend query, but Neo4j is still significantly faster. So I have shown you the requisite Twitter graph, the social graph, as an example of how to use Neo4j. But Neo4j can actually be used for some pretty advanced data modeling as well. And I want to introduce to you Sophia, which is my artificial intelligence side project. Sophia features natural language processing with semantic as well as grammatical mapping. My goal in designing Sophia is that she will be able to comprehend and even create metaphors. In short, I want her to be able to dream. So how did I model data in Sophia? Core abstract concepts are called contexts. So in my management application, here are some contexts like animal and beauty and color and difficulty. So if we look at a specific context like beauty, you can see we have these roots. Roots have a base form. Roots are basically an expression of a context. They have a base form. They have grammatical forms. So if we look at one of the roots, like beautiful, it's really easy for, they also have a positivity, which is if they're a positive expression of a context, like temperature, being hot would be a positive expression, cold would be a negative expression. So because of the positivity ranking on them, it's really easy to derive synonyms and antonyms just by comparing those rankings. So we have a list of synonyms here and some antonyms. If a word matched exactly the positivity ranking of this word, then it would show up as related. And down at the bottom, we have parts of speech. So the concept of beautiful can be expressed as an adverb, beautifully, or as an adjective, beautiful. And we have some metadata associated with those parts of speech. So beautifully modifies manner, and it's a verbal adverb. Adjective has a comparative form, which is more beautiful, and a superlative form, which is most beautiful. So how did I model this in Neo4j? We'll do a query where we look at a context and its roots, so the core concept and how it's expressed. We're going to match node A, which is a Gramercy meta context, with the name of beauty. With a relation directional to node B, which is a Gramercy meta root. And we'll return the context, the relation, and the root, and we'll limit it to 100 records. So you can see, hopefully you can read that. We have beauty in the middle, and each of those things radiating off of it is a root. Now let's go from contexts and roots all the way down to parts of speech. So in this case, we're going to match node A, which is a Gramercy meta context, with the name of beauty. With a relation directional to a Gramercy meta root. And we're going to go one layer deeper in our relation with a directional relation R2 to node C, which is a Gramercy part of speech generic. And we're going to return all of the nodes and relations that we referenced. So this is a simpler graph because we're just looking at roots for the word beauty. So we have a couple of roots hanging off of that with grammatical expressions as the green nodes. The red nodes are the roots, and the orange node is the context. Sophia also understands ISA and HASA hierarchies, which are a way of modeling facts. So I have this fact explorer. This is a list of facts that she knows. She knows that a cat is a mammal, that a cat has fangs and a tail, that Elfie is a cat. Elfie's adorable. I wish I had a picture of her. And that animals are mammals that have fur. So we can query facts using natural language. The parser knows we're asking a question, and the context of the question is animals. It figured out the subject is cat, the verb is have, and the predicate is fangs. And the answer to does a cat have fangs is yep. Because a mammal is a living thing and an animal, in this case, two contexts come up, living thing and animal. And the fact that a cat has a tail and a cat is a mammal lets the parser know that some mammals do have tails, like cats, for example. We can also add new facts by making declarative sentences. Elfie is cool, and the response is, I'll remember that. If we take a look down at the bottom at how it parses the sentence, it knows that it's a statement. The subject is Elfie, the verb is, the predicate is cool. For the context, she knows it's an animal because Elfie has already been expressed as, the fact about Elfie is that she's a cat, and a cat is a mammal, and a mammal is a living thing. But Sophia is not able to determine what the word cool means. Cool is an expression of temperature, but also of disposition. And there's not enough context in this sentence for her to distinguish between the two. If we had additional words like she's cool and interesting, then Sophia would understand that we were talking about disposition. And again, we can ask questions that are that require inference. So is a cat cool? Because we said that Elfie is cool and Elfie is a cat, Sophia knows to say that some cats are in fact cool. So how is an ISA hierarchy structured? Let's look at another query. We're going to match node A, which is an ISA category. And a category is just a node that has relations to multiple nodes, which are called objects. With the relation F to an ISA category, with a relation F2 to an ISA component. So a component is something that makes up an object, and objects also have characteristics, which are things that describe them. So we can see that we can see how cat, mammal, and animal are connected. We can see that cats have tails and fangs, and that mammals have fur. So that's my AI project, Sophia. So for Sophia, a graph database was an obvious choice for me because of the complexity of the data that I was modeling, and it's paid off quite well. But when should you use a graph database? If your relations are complex, when the metadata around a relation is just as important as the relation itself. If your data is deeply nested, when performance is really important to you, because again, graph databases exhibit linear performance characteristics. When you want to move very quickly, because graph databases are schemaless, they allow you to change your mind quickly during development processes. And let's be honest, use a graph database if you like bright, shiny things. We're developers, we're attracted to bright, shiny objects, so we should be honest about that. So give it a try. It's a quick download. Installation takes several minutes, so you might want to grab a cup of coffee or tea. There's really good documentation. The NEO4J RB gem is very solid. The fact that it's active model compliant means that it's easy to get up and running. So new tools encourage us to explore and to play. And personally, this is how I learn best, by leaving behind my assumptions about how things are supposed to work and finding new ways to make them work. From my perspective, this is one of the best parts of being a developer, being constantly encouraged to learn and to grow. So give graph databases a try. Even if you don't end up using one in production, you'll have challenged some of your assumptions about data modeling and picked up some neat new tricks along the way. Hopefully I've inspired your curiosity and you'll go and try it out. Thank you very much.